Okay, so this is our second method. This is factoring by grouping. Okay, so that means we're pretty much going to group parts of my polynomial together and factor that and then factor the whole thing. This one I think is maybe the most complex to wrap our heads around. And I think that because if you can't find the GCF of a polynomial, then it's gonna be almost extra difficult to factor by grouping. Speaking of factoring by GCF, remember that's always the method that we factor by first. So we always try to factor by GCF first. Always try to factor by GCF first. Okay, that's always our first method, GCF. Okay, that's super important. So steps to factoring algebraic expressions by grouping. Okay, I'm not going to put it in fancy words. I'm going to try to make it as easy to follow as possible. But when I first say all of the steps, it's not going to really make sense. But so the first step is to make two groups. So you have to make two groups. Okay, what's important to remember before you can make those two groups is that your exponents have to be in order. So the exponents have to be in descending order. Okay, so your exponents have to be in a descending order, or otherwise you can't factor by grouping. Therefore, it's pretty much impossible. So now that you've made two groups, now we find the GCF of each group. So we find the GCF of each group. Now, these need to be the same. So not those need to be the same, but the GCF, when you take that out, what's left over should be equal. So I'm going to say what's left over should be equal. And again, that's not really going to make sense until we see it, okay? So once you take the GCF out of each group, there's going to be those leftover numbers, and they should be equal. And if they're not, that means your GCF wasn't right, or that it's not factorable. Okay? And then we take the GCF of the polynomials. So we take the GCF of the polynomial, aka what each group has in common, what each group shares, and aka that's really our leftovers. Okay, and then this leaves us with our resulting factor. Okay, sorry if my handwriting's a little bad. Trying my best here. Okay. So let's see this in practice. Okay, so make two groups. Exponents should be in descending order. So looking at our exponents, are they in descending order? Yes, they are in descending order, which means I can put them into two groups. And generally, those two groups are our first two terms and our last two terms. So these are our two groups, okay? So as long as it's in descending order, it's your first two terms and your last two terms. Those are our groups. So looking at these groups, we need to find the GCF. So looking at this red group or this first group, think about what is your GCF of those terms. The GCF of those terms is 2k. So when I take a 2k out of 6k squared, I should be left over with 3k. When I take a 2k from 4k, I'm left with 2. Okay, now we always put a plus sign here, no matter what. Okay, now I have to look at this next group of 2. So I'm finding the GCF. Is there a GCF between 3k and a -2? You may be thinking, no. But there is. It's the number 1. So we can take a 1 away from both of them, which doesn't really do anything, but that's okay. So when we divide each one by 1, we're left with 3k minus 2. Okay, and as I said in example 2, our leftovers should be equal. Our leftovers should be equal. Are our leftovers equal? Is 3k minus 2 equal to 3k minus 2? Yes. So that means we took out the correct GCF. And now if you're looking at this as an entire polynomial, this whole thing, 2k, parentheses, 3k minus 2, plus 1, parentheses, 3k minus 2, there is a GCF there that each part shares, right? So if you're looking at this as a group, there's 2 parts of that. If you're looking at this as a group, there's 2 parts. What's the GCF of each group now? The GCF is really that 3k minus 2. So we're pretty much taking our leftovers, and they're now their own group. And that means these leftover numbers here, this 2k and this plus 1, now make their own group. Okay? So now my other group is 2k plus 1. And now that's the answer. Okay, so again, our first step was to make it into 2 groups. As long as our exponents are in descending order, we just take the first 2 numbers and the last 2 numbers. From there, we found the GCF of those highlighted groups. We put our leftovers in parentheses. Now, our leftovers should be equal, which they were. Again, I'm putting leftovers in quotation marks because, it's not obviously what they're called, but I think that's the best way to describe them. Then we're technically taking the GCF of each group again, which should be that leftovers category, that 3k minus 2. Okay, so I want you to take a moment and try to get as far as you can in example 2. So I want you to try to get as far as you can in example 2. I'm going to put all of my work there and everything. I'm going to color code it just as I did. Okay, and I'll briefly explain it once I come back. But I want you to try it and get as far as you possibly can before you check for help. Okay, so hopefully you got 6z plus 5 and 2z squared minus 5. You may be thinking, does the order of which I wrote these 2 things matter? No, you could have them reverse. It doesn't really matter what order, as long as the signs and the numbers are the same. If any of your signs are different, your answer is wrong, okay? So that you have to make sure you take out a -5. That's really important, okay? A -5. So again, we break it into 2 groups, the first 2, the last 2. Once you break it into groups, you find the GCF of them, and that's how I got 2z squared and the -5. And then once you take out that GCF, you should have the same thing left in the parentheses. And I did. I had 6z plus 5. And now that's technically our GCF of our polynomial, so we take that out. And our leftovers, those original GCFs, get put into their own parentheses. Okay? So let's look at example 3. Okay, looking at example 3. I'm going to break it into 2 groups. 2 groups. Okay, 2 groups. Group 1, group 2. Now I'm going to take the GCF of each group. So take the GCF of each group for me. Hopefully you think, okay, this first GCF is 2. So that leaves me with 2xy plus 3. My second GCF is -1, which leaves me with x plus 24y. Now, all of these previous times, what's in the parentheses has been equal. Are what's in the parentheses equal? No. So that either tells me A, I didn't take out the correct GCF, or B, that this is prime. Okay, so I know I took out the right GCFs. So that tells me that this problem is actually prime because my leftovers, or what's in the parentheses, is not equal.